It arrived without warning, a ghost drifting between the stars. For eons, it had traveled through the absolute zero of the void, a silent pilgrim carrying secrets from a birthplace we will never know. Its journey was one of unimaginable loneliness, a flight through the crushing, silent emptiness that separates the suns. Then, after a voyage of perhaps 1 billion years, it entered our home, our solar system. On the summit of Mauna Loa, under a dome of pristine Hawaiian sky, the asteroid terrestrial impact last alert system stood its nightly watch. Atlas is not a single telescope, but a robotic network, a sleepless automated guardian scanning the heavens for threats. Its mission is humble but vital: to find the near-Earth asteroids, the stray bullets of the cosmic firing range that could pose a danger to us. It sifts through an ocean of data, a relentless digital stream cataloguing the faint and the familiar, the known comets and the local rocks. Most nights are a quiet hum of machinery and flowing information, a predictable ballet of celestial mechanics. But on this night, the algorithm flagged something new. It was a smudge, a barely perceptible mote of dust against the infinite black, an object so faint it was skirting the very edge of detection. The software with cold precision calculated its trajectory. The curve was wrong. It wasn't the gentle elliptical path of a captive of our sun. This was a hyperbola, the unmistakable sweeping arc of an intruder, an outsider. This tiny phantom was not from here. It was moving too fast, its velocity, a clear sign that it was unbound by our star's gravity, merely passing through on its way back to the interstellar deep. Following protocol, the system logged it, giving it a provisional designation 3I, Atlas. The 3I was critical, the third confirmed interstellar object ever detected. Like Oumuamua and Borisov before it, it was a priceless scientific treasure. A messenger from another star system delivered directly to our doorstep. What was it made of? What story did its chemical composition tell about the stellar nursery from which it was violently ejected so long ago? Telescopes around the world were being alerted. Astronomers, woken by automated messages, scrambled to their computers, eager for a glimpse of this rare visitor before it vanished forever. For a few precious hours, 3I Atlas was the focus of intense curiosity, a fascinating but by all accounts an entirely passive piece of cosmic debris. It was a piece of rock and ice, perhaps a few kilometers wide, a cold, inert and solitary wanderer. And then the universe shattered. Without prelude, without any physical justification, a colossal wave of energy erupted from that precise point in space. A flash of light, so violent, so profoundly powerful, it momentarily blinded high-energy observatories in orbit. This was not the gentle twinkle of a star. This was a scream, a celestial shriek of pure, unadulterated power. The alert systems at NASA's Swift Observatory and the Fermi Gamma Ray Space Telescope, designed to detect the death throes of stars, went into overdrive. Data flooded their servers, a tsunami of high-energy photons, painting a picture of an event so extreme it bordered on the divine. For 1.7 seconds, this insignificant visitor, this tiny interstellar rock, unleashed one of the most luminous gamma-ray bursts ever recorded. To understand the sheer soul-crushing impossibility of what you just witnessed, you have to understand what a gamma-ray burst, a GRB, truly is. They are not mere explosions. They are the universe's apex predators of cataclysm. For decades, we believed they had only two possible origins, two events, violent enough to forge such a celestial blowtorch. The first is the death of a truly massive star, a celestial titan, perhaps 100 times more massive than our own sun. At the end of its life, its core collapses under its own immense gravity, crushing down into a black hole. As the star's outer layers fall inward, the newborn black hole ignites, launching twin jets of matter and energy that tear through the dying star. These jets, moving at over 99% the speed of light, are what we see as a long-duration gamma-ray burst. It is the birth announcement of a black hole, a funeral pyre visible across billions of light-years. The second known cause is even more exotic, the collision of two neutron stars. Imagine two objects each more massive than our sun, but crushed down to the size of a city. Their gravitational fields are so intense, they warp the fabric of space-time itself. Locked in a gravitational death spiral, they orbit each other hundreds of times a second, shedding vast amounts of energy as gravitational waves. Finally, they collide. The resulting explosion, a kilonova, is a crucible of creation, forging most of the heavy elements in the universe like gold and platinum. And from this spectacular collision, a short-duration gamma-ray burst is born. A fleeting but ferociously powerful blast of high-energy light. These are the two approved models: the hypernova and the neutron star merger, the collapse of a giant or the collision of two stellar corpses. Both require gargantuan amounts of mass and energy. They are events on a scale that dwarfs human comprehension. They are the known titans, the cosmic behemoths responsible for GRBs. And that is the heart of our terrifying new mystery, because 3I, Atlas, was none of these things. It was not a star 100 times the mass of the Sun. It was not two city-sized stellar remnants locked in a death spiral. It was, according to all the initial observations, a quiet, frozen rock, a cosmic pebble. The energy it released in less than 2 seconds was greater than the total amount of energy our own Sun will produce in its entire 10 billion year lifetime. Let that sink in. All the light, all the heat, all the life-giving radiation of our star from its birth to its eventual death as a white dwarf was surpassed by a piece of interstellar debris in the blink of an eye. It's a contradiction so profound, it's like watching a single grain of sand detonate with the force of a supernova. It's like finding a child's toy that can power a galaxy. It is by every metric we possess physically fundamentally impossible. The scientific community was thrown into a state of stunned disbelief. The first assumption, the only rational assumption, was that it was a mistake, a coincidence of staggering improbability. Perhaps the GRB came from a distant galaxy that just happened to be perfectly aligned from our point of view with the interstellar object. An optical illusion on a cosmic scale. Frantic calculations were made. Teams around the world raced to pinpoint the origin of the gamma rays, using the tiny time delays between when the pulse hit different orbiting observatories. They triangulated its position with breathtaking accuracy. The verdict was unanimous and horrifying. The source was not a background galaxy billions of light years away. The source was local. It was inside our own solar system. The gamma-ray burst came from precisely the same coordinates, the same tiny patch of sky as 3I, Atlas. There was no mistake. The phantom and the explosion were one and the same. The news rippled through the world of astrophysics, not like a wave, but like a shockwave. It broke everything. Decades of carefully constructed theories about the universe's most extreme phenomena, the elegant models of stellar evolution and high-energy physics, were rendered instantly terrifyingly obsolete. It felt like a violation. The universe, which we thought we were beginning to understand, had just shown us a card from a deck we didn't even know it was playing with. The foundations of our cosmic understanding began to crumble. If a small, seemingly inert object can generate this kind of energy, what else have we misunderstood? Our neat categorization of the cosmos, with its predictable stars and orderly physics, was suddenly revealed as a dangerously incomplete map. We were explorers who had mistaken a single island for the entire world, only to watch a sea monster rise from the depths. This event forces us to confront questions that strike at the very heart of reality. Is there a new type of physics we have yet to discover? An unknown mechanism for storing and releasing energy on a scale we cannot fathom? Perhaps 3I, Atlas, wasn't a rock at all. Perhaps it was something else entirely masquerading as a simple wanderer. Was it a piece of some exotic object, a fragment of a quark star, or a shard of a strange matter nugget? Objects that exist only in the wildest theories. Could it have been a primordial black hole, a relic from the Big Bang that finally evaporated in a final violent flash of Hawking radiation? The mathematics of that don't quite line up, but in the face of the impossible, every theory, no matter how outlandish, must be brought to the table. The silence from the scientific community in the immediate aftermath was deafening, a shared moment of intellectual paralysis. How do you begin to explain something that your science says cannot happen? And then the most unsettling possibility of all began to be whispered. A thought so profound, so paradigm-shifting, it is almost too frightening to consider. The profile of the gamma-ray burst was odd. It was clean, almost too clean. Natural cosmic explosions are messy affairs, with complex energy signatures and lingering afterglows across the electromagnetic spectrum. But the burst from 3I, Atlas, was a surgical strike. A narrow, focused, incredibly efficient pulse of energy. It almost looked engineered. Was this a natural phenomenon at all, or was it a message, a warning, a weapon being fired? Could this interstellar object have been a probe, a piece of technology so advanced it appears to us as a miracle or as a violation of natural law? This is the precipice on which we now stand, staring at a single data point that threatens to rewrite the story of the universe. An event that is either a profound new discovery about the nature of reality itself, or the first sign that we are not and have never been alone. The visitor 3I, Atlas, is gone now. Having delivered its impossible proclamation, it continued on its trajectory, fading back into the darkness. It will never return. It has left behind only a single searing question burned into our consciousness. What did we just see? The object itself is beyond our reach, but its echo remains. The light from its impossible detonation is a clue, a cosmic fingerprint that we must now painstakingly analyze. To solve the greatest mystery of the 21st century, we cannot chase the messenger who has already vanished into the night. We must instead decipher the message. To understand this impossible crime against physics, we must first understand the weapon. We must journey back to the very beginning of our search for these cosmic ghosts, to the Cold War era of nuclear paranoia and orbiting spy satellites. For it was there in the tense twilight struggle between superpowers that we first accidentally stumbled upon the terrifying, beautiful, and profoundly misunderstood phenomena known as gamma-ray bursts. What happens when the universe screams? Across the silent, unforgiving vacuum, a message of pure violence is broadcast. A flash of energy so fantastically powerful, it momentarily outshines entire galaxies. It is not a sound you could ever hear, but an outburst of the most energetic light in existence, a torrent of gamma rays carrying an apocalyptic fury. For a few fleeting seconds, this ephemeral beacon, this cosmic shriek, can release more energy than our sun will generate over its entire 10 billion year lifetime. This is a gamma ray burst, the universe's ultimate expression of cataclysm. It is the signature of cosmic death on a scale that defies human comprehension. A declaration that something of truly immense power has just been annihilated. And for decades we believed we understood the culprits. We thought we knew the titans capable of unleashing such fury, the monsters dwelling in the cosmic deep, whose death throes were violent enough to send these ripples of destruction across billions of light years. To create such an event, you need to tear apart the very fabric of existence. You need a crucible of unimaginable temperatures and pressures, an engine of gravitational collapse so extreme it borders on the surreal. The prime suspect has always been the hypernova, the death of a truly colossal star, a behemoth at least 30 or 40 times more massive than our own Sunday. Imagine a star so vast its outer layers would swallow the orbit of Jupiter, a gargantuan sphere of plasma burning through its hydrogen fuel with an insatiable appetite. For millions of years it lives as a brilliant blue giant, a cosmic lighthouse in its galactic neighborhood, but its size is its doom. Deep within its core, the furnace where elements are forged begins to sputter. The outward push of fusion energy, the only force holding back the star's own crushing gravity, finally falters. In less than a second, the core collapses. It doesn't just shrink, it implodes with terrifying velocity, a quarter of the speed of light crushing down into an object of impossible density. What happens next is not an explosion in the traditional sense, but an obliteration from within. The core collapses past the point of no return, past the limits of matter itself, and is reborn as a stellar mass black hole. This newborn singularity, this gravitational demon, immediately begins to feed. The star's own inner layers, which were racing inwards during the collapse, now find themselves spiraling into the maw of the black hole, forming a superheated, swirling disk of doomed matter. This accretion disk becomes a cosmic dynamo. Twisted and accelerated by magnetic fields, 1 trillion times stronger than Earth's 2 jets of plasma and energy, are launched in opposite directions from the poles of the black hole. These are not mere flares. They are celestial blowtorches of almost pure energy moving at 99.9% the speed of light. They are the gamma ray burst. The rest of the star still falling inwards is pierced by these jets, which tunnel their way out like a bullet fired through an apple. As they erupt into interstellar space, they finally become visible to us, a focused, blindingly bright beam of gamma radiation. If you are in the path of that beam, even from across the galaxy, you witness the brightest event in the known universe. The star itself is gone, devoured by its own progeny. Its legacy, a brief, terrible flash that tells a distant world a monster has died. There is another way, a second path to such celestial annihilation, born not from a singular death, but from a deadly embrace. Imagine two neutron stars, the collapsed corpses of suns that were massive but not quite massive enough to form black holes. Each is a city-sized sphere of matter so dense that a single teaspoon would weigh 1 billion tons, a solid nucleus of neutrons held together by a force that almost defies physics. For eons, these two stellar zombies can orbit each other in a graceful, silent waltz, but their dance is not forever. With every pass, they radiate away energy in the form of gravitational waves, subtle ripples in the fabric of space-time itself. This loss of energy causes their orbits to decay, pulling them closer and closer together in an inexorable spiral. Millimeters per year become meters per year, then kilometers per second. The space between them churns and warps a gravitational vortex of terrifying power. In the final moments, they are whipping around each other thousands of times per second, their immense gravitational fields tearing strips of neutron-rich matter from each other's surfaces. The collision is an event of such concentrated violence it is almost impossible to picture. Two city-sized objects, each more massive than our Sun, merge into one. The result is a brief hypermassive neutron star that immediately collapses into a black hole, or perhaps for a fraction of a second forms an even more exotic object known as a magnetar. But the outcome is the same, a catastrophic release of energy. This is a shorter, sharper scream than that of a hypernova, a burst of gamma rays lasting less than 2 seconds, but it is no less potent. In that instant of merging, the collision also flings out a vast cloud of that incredibly dense neutron-rich material. It is in this debris, this cosmic shrapnel, that the universe performs its most profound alchemy. The searing heat and pressure of the merger cook these neutrons into the heaviest elements in the cosmos: gold, platinum, uranium. Every piece of jewelry you have ever worn, every precious metal we mine from the Earth was almost certainly forged in the unimaginable violence of a neutron star merger, the ghost of a gamma ray burst from long ago. So these were our culprits. The collapsing titans and the merging corpses, events defined by immense mass, by stellar evolution, by the raw power of gravity converting matter into energy on a scale that built the very elements of our world. They were the only phenomena we knew that had the sheer gravitational might, the right physics to generate a gamma ray burst. They were the bedrock of our understanding. And then, into this violent cosmos of predictable monsters came the phantoms. We knew they were out there adrift in the great dark between the stars. For centuries we had theorized about objects cast out from other solar systems, ancient wanderers on journeys lasting millions, even billions of years. Comets and asteroids born around a different sun, ejected by the gravitational chaos of their home systems, destined to sail silently through the interstellar void. Finding one was a dream, a chance to touch a piece of a completely alien world. In 2017, that dream became a reality. Telescopes picked up a faint point of light, moving in a way that was utterly wrong. It wasn't orbiting our Sunday. Its trajectory was a hyperbola, a clear indication that it was coming in fast, swinging past our star and heading back out into the void, never to return. We named it Oumuamua, a Hawaiian word for a messenger from afar arriving first. It was a revelation. But it was also deeply strange. It was small, perhaps a few hundred meters long, and tumbling end over end. It reflected sunlight in a peculiar way, suggesting a dark, reddish, elongated shape. Crucially, it showed no signs of being a comet. There was no fuzzy coma, no tail of gas and dust. It appeared to be an inert piece of rock or metal, a silent, solitary shard from another star's shattered planet, a ghost ship passing in the night. 2 years later, a second visitor arrived. This one, named 2I, Borisov, was more familiar. It looked and behaved exactly like a comet from our own solar system, just one that happened to be from somewhere else. As it neared the sun, the warmth caused its ices to sublimate, creating a magnificent coma and tail. We could even analyze the chemical composition of its outgassing, getting our first real taste of the primordial materials that build planets around other stars. Borisov was a cosmic iceberg slowly shedding its outer layers under the gentle heat of our sun, a predictable and beautiful spectacle. Between Oumuamua and Borisov, a clear picture of these interstellar visitors began to form. They were what we expected them to be: cold, ancient, and fundamentally passive relics. They were messengers, yes, but they delivered their messages in whispers. They told their stories through the faint light they reflected through the gentle streams of gas they bled into space. They were interesting because of their origin, not because of any inherent power. They were celestial flotsam debris from distant shores, not actors on the cosmic stage. The energy they dealt with was minuscule, the gentle push of solar radiation, the subtle warmth of a nearby star. To even think of connecting these quiet wanderers with the apocalyptic violence of a gamma-ray burst was not just wrong, it was nonsensical. It would be like suspecting a falling snowflake of creating a volcanic eruption. The two phenomena belonged to completely different universes of physics. One was the domain of gravitational collapse and stellar death, the other, the realm of ice and rock and reflected light. Then, on a quiet Tuesday, a routine survey telescope in Chile, part of the Asteroid Terrestrial Impact Last Alert System, or ATLAS, catalogued another faint smudge of light moving on a hyperbolic trajectory. It was given the designation 3I, ATLAS, the third confirmed interstellar object. Astronomers around the world turned their attention to it, expecting to see another Oumuamua or Borisov. They began taking spectra, measuring its brightness, calculating its path with ever greater precision. It appeared to be a fairly large object, perhaps several kilometers in diameter, a dark, icy body on its one and only pass through our solar system. For weeks, it behaved exactly as predicted, a silent traveler from an unknown shore, slowly brightening as it fell toward the Sunday. And then, without any warning, the universe screamed again. Satellites designed to watch the sky for the telltale flash of high-energy radiation were triggered. Gamma-ray telescopes from Earth's orbit to deep space swiveled to lock onto a sudden blinding point of light. It was a classic gamma-ray burst, an eruption of energy so immense it briefly registered as one of the brightest objects ever recorded. An event that signaled the death of a star or the collision of stellar cores. But the data made no sense. The frantic calculations of astronomers and physicists led them to a conclusion that was by all known laws of science completely and utterly impossible. The burst wasn't coming from a distant galaxy billions of light years away. It wasn't the signature of a dying stellar titan. The coordinates, precise and unquestionable, pointed directly, impossibly, at the faint smudge of light moving through our own solar system. The source of the universe's most powerful type of explosion was 3I, Atlas. A cold, dark, icy wanderer had just unleashed the energy of a supernova. A frozen rock, a passive drifter, had somehow generated a force that should only be possible in the heart of a collapsing star, 40 times the mass of our Sunday. It was like watching a raindrop hit the ocean with the force of the asteroid that killed the dinosaurs. It was a fundamental violation of everything we thought we knew. The physics that governs the cosmos, the very rulebook that defines what is possible and what is not, states that this cannot happen. And yet the evidence was undeniable. The silent messenger had shrieked with the voice of a dying god. The profound, terrifying question was no longer what these interstellar visitors were made of, but what they were capable of. The mystery of 3I Atlas had begun a mystery that threatened to shatter our understanding of the universe itself. What in the cosmos is this object, and how did it do the impossible? That fleeting, impossible spike of high-energy radiation was not an ending, it was a beginning. A cosmic gunshot in the dead of night whose echo would not just ripple across the solar system, but would detonate within the heart of human understanding itself. In the sterile, quiet control rooms of gamma-ray observatories orbiting high above the Earth, the silence was the first thing to break. An automated alert, a digital shriek buried in a mountain of monotonous background noise, screamed for attention. It was a signal with no subtlety, a brute force announcement that somewhere out in the unimaginable dark an event of ferocious power had just transpired. The initial reaction for the few graduate students and night shift astronomers who first saw it was not excitement. It was confusion tinged with the professional skepticism that is the bedrock of all good science. Gamma-ray bursts, or GRBs, are detected every day. They are the distant death cries of colossal stars or the violent mergers of city-sized stellar corpses. But this one was different. Its profile was peculiar. The energy spectrum was jagged, unnatural. The intensity was almost absurdly high for its apparent duration. A ghost in the machine, perhaps, a sensor glitch. The protocols, however, are absolute. Within seconds, the gamma-ray coordinates network, a silent global nervous system connecting telescopes of every kind, crackled to life. A bulletin stripped of all emotion and containing only the raw coordinates flashed across screens from the high deserts of Chile to the frozen plains of Antarctica. This was the starting pistol for a frantic worldwide race against time. The afterglow of a GRB, the fading ember of the initial explosion, is breathtakingly ephemeral. It is a ghost made of X-rays, visible light and radio waves that blooms and then vanishes, often in a matter of hours or days. To miss it is to lose the key to understanding the cataclysm that birthed it. Every second of delay meant precious photons, messengers from the blast, were lost forever into the void. Across the planet, a synchronized and yet chaotic ballet began. Robotic telescopes, unhindered by human fatigue, received the coordinates and immediately swiveled their immense optical assemblies, their mechanical eyes turning to a tiny, unremarkable patch of sky. In mission control centers, astronomers were jolted awake by pagers and urgent phone calls, their minds still thick with sleep as they tried to process the alert. Schedules were torn up, carefully planned observation runs were unceremoniously cancelled. You could almost feel the collective intake of breath from the entire astronomical community as they dropped everything to chase this fleeting phantom. The first task was simple yet monumental: pinpoint the source. The initial gamma-ray detection from orbiting sentinels like Fermi and Swift could only narrow the location down to a patch of sky larger than the full moon. It's the celestial equivalent of hearing a gunshot in a sprawling city and knowing only the neighborhood it came from. To find the exact building, the exact window, you need more witnesses. You need triangulation. By comparing the precise arrival time of the gamma-ray wavefront at different satellites separated by millions of kilometers, a more refined position could be calculated. Computers churned through the timing data, their processors racing to draw intersecting arcs on the celestial sphere. The resulting error box shrank and shrank again. A new set of coordinates, far more precise, blazed across the network. Now the hunt was truly on. This new position was the treasure map. X marks the spot. Telescopes on the ground, now knowing exactly where to look, began a desperate vigil. They were searching for a new star, a pinpoint of light, where none had existed before. They stared into the abyss, waiting for the faintest glimmer, and then the first confirmation came. An X-ray telescope, its vision uniquely tuned to the high-energy aftermath of such explosions, detected a rapidly fading source right in the center of the error box. It was the smoking gun. This was real. This was happening. The X-ray data was wild, unlike the smooth, predictable decay curves of typical GRBs. It flickered erratically, dimming and then flaring back up with a menacing stutter, as if the central engine of the explosion was refusing to die quietly. Its behavior hinted at a process far more complex and unstable than the elegant physics of a collapsing star. It was a clue, a piece of the puzzle, but it only deepened the enigma. Then came the optical light. A telescope in Hawaii, perched atop the dormant volcano of Mauna Kea, captured the first visible light image. There it was, a tiny ephemeral spark, a new temporary star blazing with the fury of 1 billion suns. A spectrograph was immediately brought to bear, splitting that faint light into its constituent rainbow of colors. Within that spectrum lay the chemical fingerprints of the event, a barcode, revealing the elements forged and then ejected by the blast. But the initial readings that scrolled across the screen made no sense. They didn't show the expected signatures of heavy elements from a supernova. The composition was alien, a strange mix that seemed to defy the known recipes of stellar death. As dawn broke across the Pacific, the baton was passed to observatories in South America. The Very Large Telescope, a quartet of colossal instruments in the Atacama Desert, focused its combined power on the fading point of light. The data it gathered was of exquisite quality, but it only compounded the felony against established theory. The light was polarized in a bizarre, swirling pattern suggesting the presence of incredibly organized and powerful magnetic fields, far stronger than what a conventional GRB model could produce. It was as if we were watching not just an explosion, but the collapse of some vast, intricate magnetic structure. The final piece of the initial evidentiary puzzle came from the lowest energy part of the spectrum. Vast arrays of radio dishes like the Atacama Large Millimeter, Submillimeter Array turned their collective gaze toward the source. They were listening for the deepest, most resonant echo of the explosion, the shockwave now plowing through the interstellar medium at nearly the speed of light. They heard it, a faint, expanding whisper of synchrotron radiation. This radio afterglow was the ultimate confirmation of the blast's immense energy, but like everything else about this event, it was abnormal. It was brighter than it should have been, and its expansion seemed to be decelerating in a way that implied the surrounding space was far denser than anyone would have predicted for a random point in the void. The data was in. From the highest energy gamma rays down to the longest wavelength radio waves, the evidence was overwhelming, incontrovertible, and utterly terrifying in its implications. The global astronomical community had successfully captured a portrait of the cosmic crime scene from every conceivable angle. Now came the moment of truth. The coordinates for this unprecedented, rule-breaking cosmic explosion were plotted onto celestial charts. They were cross-referenced with catalogues of known stars, galaxies, and nebulae, the routine work of identifying the host environment of the burst. And that is when the quiet confusion curdled into sheer, unadulterated disbelief. The coordinates were not merely close, they were a perfect bullseye match. A direct one in a trillion hit on the precisely predicted trajectory of a known object. But it wasn't a massive star on the verge of collapse. It wasn't a pair of spiraling neutron stars locked in a gravitational death dance. The source of the most luminous electromagnetic event ever witnessed by humanity, an outburst that had momentarily outshone entire galaxies, was none other than 3I, Atlas. A profound, chilling silence fell over the scientific world. You must understand the sheer, monumental absurdity of this revelation. It was a violation of the established order, a piece of evidence so heretical, it felt like a prank played by the universe itself. 3I, Atlas, was for all intents and purposes a dirty snowball, a tiny inert lump of ice and rock no more than a few kilometers across, drifting silently between the stars. It possessed no internal furnace, no vast reservoir of gravitational potential energy. To claim that this insignificant interstellar vagabond had produced a gamma-ray burst was tantamount to claiming you had seen a pebble spontaneously detonate with the force of a thermonuclear weapon. It was impossible. It broke the most fundamental laws of astrophysics. The energy budget simply did not exist. A long-duration GRB, the kind this event's light curve mimicked, requires the death of a star at least 30 times more massive than our Sunday. The star's core collapses under its own immense gravity, forming a black hole while its outer layers are superheated and blasted into space as a hypernova. The energy release is a consequence of the death of a true giant. 3I, Atlas, by comparison, is not even a microscopic speck of dust next to such a star. It possesses less than a trillionth of the required mass. There is no known physics, not even in the most speculative theories, that could explain how to extract that much energy from such a minuscule object. And what of the alternative short-duration GRBs are produced by the collision of two neutron stars, the ultra-dense remnants of dead stars? This process is a gravitational catastrophe, a space-time warping event of such violence that it forges gold and platinum in its wake. But that requires two such objects, and 3I, Atlas, was traveling alone. It was a solitary wanderer, a refugee from another solar system. There was no companion, no dance partner for a terminal merger. The very classification system for these cosmic detonations, a neat binary chart that had served astronomers for decades, had just been rendered useless. This event was neither a long-duration burst nor a short-duration burst. It was something else, something other. The data that had been so painstakingly collected now seemed like a taunt. Every photon, every radio wave confirmed the impossible. The X-ray flare's erratic behavior, the optical spectrum's bizarre chemistry, the radio afterglow's strange deceleration, none of it fit. Scientists ran the models again and again, desperately searching for an error, a miscalculation, some mundane explanation that could restore order to their universe. Could it have been a background object, a distant quasar flaring up by pure astronomical coincidence, perfectly aligned with the position of 3I, Atlas? The odds were infinitesimal, statistically indistinguishable from zero. The afterglow was fading, and a fading source means a transient event, not a persistent object like a quasar. More damningly, radio observations showed the shockwave was expanding from a point source not emanating from a galactic core millions of light-years farther away. The evidence was a cage, and its bars were tightening with every new observation. There was no escape from the horrifying conclusion. This tiny, insignificant interstellar traveler, this cosmic nobody, was the culprit. The community was forced to abandon the comfortable shores of known physics and wade into a dark, turbulent sea of speculation. The neat categories and tidy explanations that had filled their textbooks were being torn to shreds before their very eyes. They had been confronted with an object that behaved with a violence that was by all rights reserved for the death of suns. The initial shockwave of the discovery, the frenetic chase for data, was now over. A new, more profound phase was beginning. The phase of acceptance. The uncomfortable, paradigm-shattering acceptance that we had just witnessed something entirely new. Something that did not fit. Something that whispered of energies and processes operating in the cosmos that we had not yet even dreamed of. The question was no longer times if times 3I Atlas had done this. The data was unequivocal. The question, the one that now kept every astrophysicist on the planet awake at night, was a single terrifying word that hung in the air like the afterglow of the burst itself times. How times? And so the silence from the models became a deafening roar. Across the globe, in the sterile humming sanctuaries of computation, the universe we thought we knew was refusing to cooperate. Every simulation, every elegant equation, sculpted to describe the death of stars and the collision of cosmic titans, crashed against the stubborn, undeniable truth of 3I, Atlas. They threw everything at it, the fury of a hypernova, the gravitational shriek of merging neutron stars, even the speculative death rattle of a black hole swallowing a world. Each scenario, rendered in trillions of calculations per second, produced a ghost, a pale imitation of the energetic violence our telescopes had just witnessed from that lonely wanderer. The light was wrong, the energy was wrong, the very character of the event felt alien, a violation of the established cosmic legal code. This wasn't merely a failure of prediction, it felt like a betrayal. Astrophysics, a discipline built upon the foundational belief that the laws of physics are universal, was facing a rebellion. Here was an object born in the cold primordial nursery of our own solar system that had travelled out into the interstellar dark for millions of years, only to return and detonate in a way that defied everything we had learned from the farthest, most violent reaches of the cosmos. The community found itself adrift in a sea of perfect yet paradoxical data. The signal was crystal clear, a high-fidelity scream across space, yet its meaning was hopelessly, maddeningly opaque. For weeks, the argument was circular, a frantic intellectual orbit around the same impossible fact. It looked like a gamma-ray burst. It shone with the power of one, but its parentage, its origin story, was an orphan's tale with no beginning. Then, slowly at first, like the turning of a great tide, a dangerous new question began to be whispered in the corridors, posed hesitantly in late-night video calls across continents. It was a question that bordered on scientific heresy. What if we were asking the wrong thing entirely? What if the problem wasn't that we couldn't find the right times, cause times for a gamma-ray burst from this object? What if the event wasn't a gamma-ray burst at all, not in any sense we had ever categorized? To even suggest this was to abandon the charts to sail willfully into a vast, unmapped ocean of uncertainty. The gamma-ray burst classification is one of the pillars of high-energy astrophysics, a spectrum of violence with known actors. Saying this wasn't one of them was like a biologist finding a creature with warm blood and feathers that also photosynthesized and breathed water. It would break the very kingdom of life itself, yet anomalies demand radicalism. And as the old hypotheses withered under the glare of the data, new fragile ideas began to sprout in the fertile ground of failure. Perhaps 3i, Atlas, hadn't been the victim of some external catastrophe. Perhaps it wasn't a passive player struck by a cosmic hammer. The revolutionary thought was this: what if the cataclysm was not something that times happened to times 3, I, Atlas, but something that times arose from within times it? What if the object was not the stage but the actor, and the play itself? This shifted the entire focus of the investigation, turning the telescope of inquiry from the vast empty space around the object inward into the impossibly dense unknown heart of 3i, Atlas itself. A place of pressures and temperatures so extreme our physics could only offer tentative, trembling guesses as to its nature. It was a pivot from astronomy to something far more fundamental, a journey into the subatomic soul of a dead piece of rock and ice. The key that unlocked this new terrifying door was not found in the initial blinding flash of the explosion. That was too chaotic, too saturated with raw power. The real clue, the Rosetta Stone for this impossible event, was hidden in the aftermath, in the long fading tail of the burst, the light curve. In astrophysics, a light curve is the epitaph of a cosmic event. It is the biography of a star's death written in photons over time. A standard gamma-ray burst has a familiar, almost poetic signature. A rise of unimaginable speed, a chaotic, jagged peak of peak fury, and then a long, graceful, and most importantly, smooth decline. An exponential decay like the ringing of a celestial bell, fading slowly and predictably into the silence of the void. It is the signature of an explosion, a singular catastrophic event after which the shrapnel and energy simply spread out and cooled down. It is the physics of an ending, but the light curve from 3i, Atlas, was not an ending. It was a conversation. A team at the Max Planck Institute, tasked with the mind-numbing work of cleaning and calibrating the photon data minute, by excruciating minute first saw the discrepancy. On their screens, the initial peak was there as violent as any ever recorded. The decline began as expected, a steep plummet from impossible brightness. But then, it stopped. Where there should have been a smooth downward slope, the graph suddenly flattened out into a perfect horizontal plateau. For an astonishing 72 seconds, the object's light refused to fade. It held its breath, pouring out energy at a constant, unwavering rate, a celestial blowtorch held steady against the darkness. This was not the echo of an explosion. This was the hum of an engine that was still running long after the primary detonation. And then it got stranger. After those 72 seconds of eerie, unnatural calm, the light curve didn't resume its gentle fade. It began to pulse, subtle at first, then growing in amplitude, a series of smaller, rhythmic bursts nested within the larger decay. It was a cosmic heartbeat, a shudder running through the dying embers of the cataclysm, each pulse an injection of new energy into the system. And finally, after this bizarre, fluctuating performance, the light did not fade to black. It simply vanished. The cutoff was absolute, a vertical drop on the graph, so sharp it looked like an instrument failure. One moment 3i, Atlas, was blazing with the light of a billion suns. The next it was gone as if a cosmic switch had been thrown, plunging it back into utter blackness. The bell had not faded, it had been shattered mid-ring. This light curve was more than an anomaly. It was a manifesto. It was a message written in the language of high-energy physics that a simple singular explosion could not possibly be the answer. The plateau, the pulses, the instantaneous cutoff, this complex structured behavior screamed of an ongoing internal process. A mechanism. The implications were staggering, sending waves of disbelief and frantic excitement through the global scientific community. The burst from 3i, Atlas, was not the shrapnel from a grenade. It was the exhaust from a complex machine that had for a few minutes run wild before catastrophically failing. The question was no longer what blew it up, But what times was? Time's the engine hiding inside this frozen interstellar refugee. And with that, the physicists took over from the astronomers. The problem descended into the quantum realm, into the strange and violent world of matter under duress beyond human comprehension. Out of this theoretical ferment, two terrifying and extraordinary hypotheses emerged, each one pushing the boundaries of known science. The first centered on a concept so esoteric it sounds like science fiction, an explosive phase transition. We see phase transitions every day, water freezing to ice, steam condensing into liquid. These are gentle, predictable shifts in the arrangement of atoms and molecules, but under the colossal pressures deep inside a body as massive and dense as 3I, Atlas matter behaves in very alien ways. Physicists have long theorized that if you squeeze normal matter protons and neutrons hard enough, it can collapse. The very walls between the subatomic particles could dissolve, forcing them to merge into a new ultra-dense state of being, a substance known as strange matter or quark-gluon plasma, a material so stable, so energetically favorable, that its existence is like a gravitational sinkhole at the bottom of reality. The hypothesis proposed that the core of 3I, Atlas, for billions of years, had been teetering on the brink of this transformation, a cosmic pressure cooker primed to go off. Perhaps a slight change in its trajectory, a subtle gravitational squeeze as it neared our sun was the final nudge it needed. In a fraction of a microsecond, a tiny seed of its core may have undergone this catastrophic phase transition, collapsing into strange matter. This was not a gentle freezing. This was a subatomic coup d'etat. The new hyperdense matter would have been a catalyst instantaneously and violently converting all adjacent matter it touched. A wave of physical law rewriting itself would have torn outward from the core at nearly the speed of light. The initial gamma-ray burst was the scream of this conversion, the release of binding energy from quadrillions of tons of matter being fundamentally rearranged. This theory, beautiful in its horror, also explained the light curve. The 72-second plateau was not an engine in the conventional sense. It was the duration of the conversion wave, the time it took for the phase transition to consume the entire object from the inside out. A steady, ongoing process of annihilation and rebirth, releasing a constant, brilliant stream of energy. The subsequent pulses were the aftershocks, the new ultra-dense object quivering and settling into its final stable state, like a bell struck with an impossibly hard hammer. And the sharp cutoff. That was the moment the conversion was complete. The fuel was spent. The reaction was over. Silence. The object we knew as 3I, Atlas, had in a very real sense committed suicide and been reborn as something entirely new. A silent, dark sphere of exotic matter, a true strangelet, now continuing its journey through our solar system. We weren't looking at the debris of a comet anymore. We were tracking the corpse of a physics experiment. The second hypothesis was no less radical, but approached the problem from the direction of gravity and structural mechanics rather than quantum physics. It imagined 3I, Atlas, not as a uniform body, but as a complex gravitationally bound agglomerate of incredibly dense, disparate materials, a celestial rubble pile of unimaginable density. Perhaps its core contained a captured shard of a neutron star, or a microscopic primordial black hole, a relic from the Big Bang. For eons, this impossibly complex system had maintained a delicate equilibrium, its own immense gravity, the only thing holding its warring internal components together. It was a gravitational gyroscope spinning in perfect, deadly balance. But as it approached our sun, the subtle tidal forces, the gentle gravitational pull of our star began to tug at this delicate structure. The disturbance, infinitesimally small at first, began to cascade. One component shifted, throwing the entire gravitational balance into chaos. What followed was not an explosion in the chemical or nuclear sense, but a complete and total structural failure on a planetary scale. A gravitational unraveling. Internal sections, no longer perfectly balanced, would have crashed into each other with relativistic forces, shearing and compressing matter in ways that would flash heat it to trillions of degrees. This was the source of the gamma rays. Not a single event, but a chain reaction of internal gravitational collapses and collisions. A planetary body tearing itself apart from the inside out, powered by the release of its own potential energy. The bizarre light curve under this model was the signature of this cascade failure. The plateau was a period where two massive internal plates were grinding against each other, generating a steady stream of friction and energy before they ultimately gave way. The pulses were subsequent smaller collapses, echoes of the main event, as the entire object reconfigured its shape, a mountain range collapsing into a new, more stable form. The final sharp cutoff marked the moment that the object finally settled the internal avalanche, coming to a sudden final rest. 3I, Atlas, hadn't transformed. It had simply and utterly broken. Both hypotheses were terrifying. One suggested that matter could spontaneously rewrite its own rules in a blaze of energy that could sterilize a world. The other implied that objects of immense gravitational complexity could be ticking time bombs, capable of disintegrating with a violence that mimicked the death of the most massive stars in the universe. For the first time, scientists were looking at the data not with confusion, but with a dawning, chilling sense of understanding. These were no longer just random theories. They were frameworks, the first blueprints of a new and previously unknown chapter of physics. They were the only explanations that honored the ghost in the machine, the strange stuttering heartbeat in the light curve's fading glow. The messenger had delivered its impossible structured message from the darkness. The community now stood on a precipice, forced to accept that to understand what 3I, Atlas, had become, they would have to venture far beyond the light of familiar stars into the terrifying new physics of the ultra-dense and the utterly unknown. What terrifying language was this object speaking, and what new chapter of the cosmic story was it forcing us to read? And so the idea was on the table. A suggestion so contrary to established thought, so audacious in its implications, that for a moment it seemed to hang in the silent auditoriums and sterile laboratories like a physical weight. It was not met with immediate acceptance, nor was it dismissed with derision. Instead, it was greeted by something far more telling, a profound, unsettling quiet. The silence of minds stretched to their breaking point of careers, spent charting a cosmos that suddenly felt alien and new. This proposal, born from the ashes of every failed conventional explanation, was a key that might unlock the mystery of 3I, Atlas. But it was also a key that threatened to open Pandora's box, unleashing a universe far more violent and far more strange than we had ever dared to conceive. The comfortable maps of astrophysics, so meticulously drawn over centuries of observation, seemed to curl and burn at the edges of this single terrifying thought. How could an object so small a mere wanderer between the stars become a celestial blowtorch, powerful enough to sear itself into our history? The hypothesis offered a name, a potential mechanism, but it left the most crucial question unanswered. How was such a thing physically possible? The challenge was not merely one of scale, but of fundamental physics. A gamma-ray burst is the signature of cosmic cataclysm, the death cry of a colossal star collapsing into a black hole, or the collision of two neutron stars in a gravitational death spiral. These events unleash more energy in seconds than our sun will produce in its entire 10 billion year lifetime. They are the universe's apex predators. To suggest that 3I, Atlas, an object barely a few kilometers across, could mimic such a display was like claiming a firefly could outshine a supernova. It violated a sacred law of cosmic proportion. The energy had to come from somewhere, and the sheer density of power required was staggering, a concentration of force that our understanding of matter simply could not accommodate within such a tiny volume. Physicists returned to their whiteboards, their equations, looking back at them like mocking hieroglyphs. The numbers refused to cooperate. Compressing that much potential energy into an object of that size and mass would require conditions that should not exist outside the infernal heart of a stellar remnant or the first picosecond of the Big Bang itself. It would require a new state of matter, something beyond our standard model. This is where the real work began, in the humming, refrigerated halls of the world's supercomputing centers. If our current physics couldn't build this monster on paper, perhaps a simulation could. teams of computational astrophysicists began constructing a digital twin of 3I, Atlas, not as the inert icy body we observed, but as the theoretical time bomb the new hypothesis demanded. They had to throw out the old assumptions, tearing down the very scaffolding of what an interstellar object could be. Was it a uniform, solid, porous aggregate? Or was it something more complex, a geological Trojan horse, smuggling an impossible core across the interstellar void? They began to model it as a layered object, a cosmic geode with a mundane, chondritic crust hiding a heart of unimaginable physics. The first simulations were spectacular failures. In one run, the object simply disintegrated under its own theoretical density, its gravitational stresses tearing it apart before it could even enter our solar system. In another, the trigger mechanism, a simulated interaction with a particle in the solar wind, caused a pathetic fizzle, a brief spark of energy that was a pale ghost of the observed gamma-ray burst. Thousands of digital universes were born and died in the silicon hearts of these machines, and each one screamed the same answer: impossible. The debate intensified, spilling out from peer-reviewed journals into heated late-night conference calls and frantic email chains. One camp argued the hypothesis was a dead end, a fantasy born of desperation. They insisted there had to be a flaw in the original observation, a bizarre atmospheric distortion or an instrumental glitch that mimicked a GRB. They clung to the known, to the comforting stability of accepted physics, arguing that an extraordinary claim required truly unassailable evidence, which we simply did not have. But the other camp, invigorated by the sheer inadequacy of any other explanation, pushed back. The data from the gamma-ray observatories was robust, confirmed by multiple independent satellites. The event was real, therefore our understanding had to be what was flawed. They argued that the universe had no obligation to conform to our textbooks. Perhaps they ventured 3I. Atlas was not an anomaly but a messenger, a herald of a population of objects we never knew existed precisely because we lacked the framework to even imagine them. They were cosmic depth charges silently drifting through the galaxy, their true nature hidden, until a chance encounter or an internal decay finally lit the fuse. Driven by this conviction, the simulation teams went back to work, this time with a more radical approach. They began to tweak the fundamental constants within their digital cosmos, asking not, how can this happen with the physics we know, but what physics would be required for this to happen? They introduced hypothetical particles, states of matter theorized but never detected, such as strangelets or fragments of quark-gluon plasma relics from the universe's fiery birth. They modeled a core held in a state of precarious equilibrium, a phase change trigger that could be tripped by the slightest gravitational nudge from Jupiter, or even a subtle thermal shock as it approached our sun. For weeks, the results were the same, failure after failure. And then one morning in a darkened lab in Geneva, it happened. A single simulation out of tens of thousands did not fail. It blossomed. On the screen, the digital 3I, Atlas, with its core of hypothetical hyperdense matter, drifted through a simulated Oort cloud. It passed a small, unseen icy body, and the minuscule gravitational perturbation was all it took. The core's delicate balance shattered. The simulation showed a cascade of exotic particle decay, a runaway chain reaction that converted a fraction of the core's mass directly into energy with terrifying efficiency. A collimated jet of gamma rays, a tightly focused beam of pure radiation, erupted from the object's pole. The light curve, the energy spectrum, the duration, it was a perfect match. An eerie digital echo of the event that had baffled the world. The successful simulation was not proof, but it was a plausibility roadmap. It was a ghost of a chance, and it sent a terrifying shockwave through the astronomical community. If this model was even remotely close to the truth, then the empty spaces between the stars were not so empty after all. Our galaxy could be seeded with these objects, millions of them, perhaps billions, all silent, all dark. They would be the ultimate cosmic sleepers, indistinguishable from a common asteroid or comet, until the moment of their detonation. The implications were staggering, forcing a wholesale re-evaluation of celestial mechanics and galactic history. We had always envisioned cosmic threats as large, predictable things, a stray asteroid on a clear trajectory, a nearby star going supernova with millennia of warning. But this was something new, a hidden threat, an invisible population of stellar shrapnel that could transform a quiet patch of sky into the most violent place in the universe with absolutely no warning. It suggested that space was not a grand, empty cathedral, but a minefield. And we had just watched by sheer chance one of the mines go off. This new lens immediately prompted a frantic search through archival data. Astronomers began to pull up records of other unexplained transient events, cosmic flickers and flashes that were once dismissed as statistical noise or instrumental errors. There was the infamous "Oh my God" particle of 1991, an ultra-high-energy cosmic ray with an energy level that defied all conventional sources. Could it have been the result of a nearby smaller version of the Atlas event? Then there were the countless fast radio bursts, or FRBs, brilliant but fleeting pulses of radio waves, many of which had no identifiable galactic source. For years, their origin has been one of the field's greatest puzzles. Now scientists began running the numbers, checking for correlations. Could some of these orphan FRBs be another facet of these detonating interstellar objects, a different kind of shrapnel from their internal cataclysms? Old mysteries once relegated to the dusty backshelves of astrophysics were suddenly imbued with a startling new relevance. It felt as if we had discovered a Rosetta Stone for cosmic weirdness, a single unifying theory that might explain a whole host of celestial apparitions that had long haunted the fringes of our understanding. This led inevitably to the fringes of theory itself. Once the door to new physics had been opened, it was impossible to close. The intense debates over the simulation's validity bled into even more profound, more philosophical territory. If 3I, Atlas, was a shard of something extraordinary, what was the original object? Some theorists proposed it was a fragment from the collision of two quark stars, hypothetical bodies, even denser than neutron stars. Such an event would be so rare as to be almost legendary, yet it would seed the galaxy with precisely these kinds of hyperdense projectiles. Others went further, invoking concepts from string theory and quantum gravity. They speculated that these objects could be macroscopic chunks of dark matter, not interacting with our universe except under very specific violent conditions. It was a theory that was both elegant and untestable, placing the phenomenon just beyond our scientific reach. And then there were the most unsettling ideas of all, whispers of objects that were not native to our universe but punctures from another brain, fragments of a cosmos with entirely different physical laws that had somehow bled through into our own. These were the conversations happening now, not just in the mainstream but in the vanguard of theoretical physics. The event had shattered the consensus, creating a schism between those who sought to patch our existing theories and those who believed it was time to build a new one from the ground up. The scientists grappling with this mystery were no longer just astronomers. They were explorers, mapping a coastline that kept changing with every new wave of data. They had a working hypothesis, a simulation that glowed with promise, and a cascading set of implications that reached into every corner of their field. The universe they had studied their whole lives had been a predictable if majestic place governed by laws they felt they were on the verge of mastering. But 3I, Atlas, had ripped that tapestry apart. It revealed that the threads of reality were woven into a pattern far more complex and perhaps far more dangerous than they had ever known. They now had a theory that worked, a story that fit the facts, but it was a story of a hidden, violent cosmos filled with dark travelers on unknown trajectories, and it led to the next most urgent question of all. If this object was not a unique monster, but just one member of a vast unseen clan, how in the universe do you go about finding the next one before it finds you? From the intellectual wreckage of 100 invalidated hypotheses, a new kind of quiet began to descend. The frantic global clamour of scientific debate, which had raged for months across journals and teleconferences, was finally softening its discordant notes, slowly resolving into a single resonant chord of understanding. The fog of uncertainty that had shrouded the final violent moments of 3I, Atlas, was beginning to part, not with a sudden gust of wind, but with the patient, relentless pressure of accumulated evidence. For weeks we had been lost in a hall of mirrors where every reflection, every theory seemed plausible for a moment before dissolving into inconsistency. We had entertained the notion of exotic, unstable matter within the comet itself, a kind of primordial bomb packed in ice waiting for the sun's warmth to light its fuse. We had explored chain reactions of unknown chemistry, runaway internal fission, and even speculative higher dimensional physics. Each idea was a flare of ingenuity in the darkness, but each one ultimately sputtered out, unable to illuminate the full brutal scope of the event. The numbers simply refused to align. The sheer, unadulterated power of the gamma ray burst its exquisite structure, its peculiar afterglow. These were the stubborn facts upon which every elegant, self-contained theory had been broken. An internal explosion, no matter how exotic, would have been an undirected eruption, a chaotic release of energy. But the gamma rays from 3I, Atlas, were not chaotic. They were focused. They possessed a terrifying coherence, the signature of something that had been systematically and efficiently annihilated by an external force of unimaginable power. The crime scene was telling us that 3I, Atlas, was not the perpetrator of its own demise. It was the victim, and so the search turned outward, away from the comet's own composition, and towards the seemingly empty space through which it had travelled. The most outlandish idea, once relegated to the fringes of the conversation, began its slow, inexorable march towards the centre. It was a hypothesis born not of direct observation but of profound absence, the chilling possibility that 3I, Atlas, did not die alone, that it had a chance encounter, a fatal rendezvous in the dark with a silent, unseen partner. The proposal was as simple as it was terrifying. Something small, immensely dense and utterly dark had crossed the comet's path. A wanderer, a rogue object untethered from any star gliding through the interstellar void. The two leading candidates were cosmic phantoms of the highest order, a lone stellar mass black hole or its equally formidable cousin, an isolated neutron star. At first, the notion was dismissed by many as a statistical improbability, a cosmic ghost story. The space between stars is paralyzingly vast. The chance of a tiny comet itself, a lonely traveller intersecting with an object only a few kilometers across, seemed infinitesimal, a throw of the dice so unlikely as to be functionally impossible. Proponents were accused of invoking a deus ex machina, a phantom in the void to conveniently solve an otherwise intractable puzzle. But science at its best is a discipline of pursuing the improbable when the impossible is all that remains. A dedicated consortium pooling resources from observatories in Chile, Hawaii and space embarked on a task of forensic astronomy that seemed almost hopeless. Their goal was to re-examine every scrap of data tracking 3I, Atlas's journey, not for what it showed but for what it might be hiding. They were looking for a ghost in the machine, a subtle flaw in the celestial clockwork. The trajectory of a comet is a thing of gravitational beauty, a perfect, predictable arc dictated by the sun's immense pull. For months, 3I, Atlas, had followed its prescribed path with mathematical perfection. But the team began to look closer, applying new filtering algorithms and error correction models to the terabytes of positional data. They were searching for a deviation, a wobble, a minute perturbation so small it would have been lost in the noise of earlier analyses. For weeks, the search yielded nothing. The comet's path remained stubbornly, unnervingly perfect. The team was on the verge of abandoning the search, ready to concede that the invisible interloper was a fiction. But then, a young postdoctoral researcher at the European Southern Observatory, working late into the Chilean night, decided to recalibrate the analysis. Instead of looking at the comet's entire journey, she focused only on the final 72 hours before its destruction, a period when the object was moving at its fastest and would be most susceptible to a nearby gravitational influence. She magnified the dataset to a resolution never before attempted, pushing the observatory's supercomputers to their absolute limits. And there, buried deep within the signal, was the whisper they had been searching for. It was not a dramatic swerve. It was an almost imperceptible flaw, a tiny, elegant kink in the comet's perfect arc, a deviation of just a few arc-seconds less than the width of a human hair seen from 2 miles away. But it was undeniably, irrefutably there. 3I, Atlas, had been tugged gently but firmly by something unseen. It was the gravitational fingerprint of a ghost. The model was run again and again, checked and rechecked by independent teams across the globe. The result was always the same. The minute deflection in the comet's trajectory could only be explained by a close pass with a compact, massive object. The calculations gave them its approximate mass, somewhere between 5 and 10 times that of our Sunday, and its location a point in space directly on the comet's path, precisely where it had met its end. The statistical improbability had suddenly become a terrifying certainty. The phantom was real. With this ghost now given substance, the pieces of the puzzle began to snap into place with breathtaking speed. The focus shifted from the comet's trajectory to the gamma-ray burst itself. For decades, astronomers have studied a phenomenon known as a tidal disruption event, or TDE. This is the cosmic horror show that unfolds when a star ventures too close to a supermassive black hole at the center of a galaxy. The black hole's gravity, a force that grows exponentially stronger with proximity, seizes the star in an invisible grip. But this grip is not uniform. The side of the star closer to the black hole is pulled with unimaginably more force than the far side. This difference in gravitational pull, the tidal force stretches the star, distorts it, and then, in a final catastrophic act, shreds it into a long incandescent stream of plasma. This process, known as spaghettification, is one of the most violent events in the universe. As the stellar material is pulled into a swirling superheated accretion disk around the black hole, friction and magnetic fields accelerate particles to near the speed of light, focusing them into colossal jets that erupt from the black hole's poles. These jets are what we observe as brilliant transient flashes of energy, including gamma rays. The burst from 3I, Atlas, the scientists realized, was a perfect miniature of this exact process. It was not a star being torn asunder by a supermassive black hole, but a tiny comet being annihilated by a stellar mass one. It was a microtidal disruption event, a phenomenon that had been theorized but never ever witnessed. A new set of simulations was launched, this time not with stars, but with a fragile icy body just a few kilometers wide. Digital universes were coded into existence, each with a single dark wanderer, a black hole of 7 solar masses waiting silently in the void. In these virtual realities, a digital twin of 3I, Atlas, was sent on its final fateful journey. The results were nothing short of a revelation. On the screen, you could see the comet, a tiny speck approaching the point of no return. As it drew closer, the black hole's gravitational scalpel went to work. The comet's icy nucleus, a loosely bound agglomeration of rock and frozen gases, began to deform. It elongated, stretched thin like taffy, its structural integrity failing catastrophically. In a fraction of a second, the solid body of 3I, Atlas, ceased to exist. It was transformed into a diffuse, kilometers-long ribbon of dust, ice and vapor, a celestial contrail marking its own murder. This shredded material, no longer a coherent object, but a stream of particles, then fell toward the black hole. It did not fall straight in. Instead, its own momentum caused it to form a tiny, transient, and incandescently hot accretion disk. It was a scaled-down version of the disks seen around galactic centers, a momentary whirlpool of matter spinning at relativistic speeds around the event horizon. And just as the simulations predicted, this miniature disk, superheated to billions of degrees, launched its own miniature jets. The models showed 2 pencil-thin beams of energy erupting from the poles of the spinning black hole, precisely aligned and colossally powerful. The energy profile of these simulated jets, their duration, their light curve, and their eventual afterglow matched the observed data from 3I, Atlas, with an accuracy greater than 99%. It was a perfect fit. The jagged, complex signal that had baffled scientists for months was the precise multi-stage shriek of a comet being spaghettified, accreted, and then used as fuel for a cosmic blowtorch. The theory was beautiful, comprehensive, and supported by the mathematics. But science demands more than elegant theory. It demands definitive, falsifiable proof. The ghost had a gravitational signature, and its actions had a perfect theoretical model, but could it be seen? By its very nature, a lone black hole is the hardest thing to find in the universe. It emits no light. It reflects no light. It is a perfect patch of black against the black of space. You can only find it by what it does to the things around it. In this case, the thing around it, the comet, was gone. The show was over. Or was it one team of radio astronomers proposed a final audacious test? When material falls into a black hole's accretion disk, not all of it is consumed or shot out in jets. A significant portion can be flung outwards, creating a slower, expanding cloud of energized plasma. This outflow, interacting with the sparse interstellar medium, should produce a faint, slowly fading radio emission, a kind of long wavelength echo of the initial violent event. The signal would be incredibly weak, a whisper beneath a hurricane of galactic background noise. Using the Very Large Array in New Mexico, a sprawling network of radio telescopes, they pointed their dishes at the exact point in space where 3I, Atlas, had met its end. They integrated the signal for days, stacking observation upon observation using sophisticated algorithms to filter out the noise from distant quasars and nearby satellites. It was the astronomical equivalent of trying to hear a single pin drop in the middle of a stadium during a rock concert, and after weeks of patient listening they found it, a faint ethereal glow in the radio spectrum, emanating from a precise point. It was a textbook example of a synchrotron afterglow, the radio scream of electrons spiraling in a magnetic field. Its characteristics, its decay rate, and its polarization were exactly what the micro-TDE models predicted for the debris cloud of a shredded comet. This was the smoking gun. This was the voice of the victim's ghost echoing across the months, telling us not only who the killer was, but that it was still there, lurking in the darkness. The case was closed. The why had finally been answered, and in doing so, it had redrawn the map of cosmic hazards. 3I, Atlas, was not an anomaly of cometary physics. It was a casualty of celestial geography. It had, through sheer catastrophic bad luck, wandered into the hunting ground of a silent predator. It was not a bomb. It was ammunition loaded and fired by a gravitational weapon of unimaginable power. The event was not an explosion, but an execution. This revelation was a watershed moment, a paradigm shift in our understanding of the solar system's environment. We had discovered a new extreme cosmic process, one that happens silently and invisibly until an unlucky traveler crosses its path. The universe, it turned out, had more ways to kill you than we had ever imagined. We had solved the mystery of one comet's death, but in doing so, we had uncovered a far more profound and unsettling truth. The dark spaces between the stars are not empty. They are haunted, and now we had proof. The immediate question that ricocheted through the astronomical community was as obvious as it was chilling. How many more of these things are out there? How many of these lonely wandering singularities, these remnants of dead massive stars, are drifting through our galactic neighborhoods silent and unseen? We had stumbled upon one by accident. Its existence implies the presence of many, many more. A new census of the cosmos was needed, a search not for the light but for the shadows. We needed to map the distribution of these invisible threats to understand their orbits, to predict their paths. Because 3I, Atlas, proved that the greatest dangers in the universe are not the things you can see coming. They are the things that have been waiting in the dark all along, a fundamental hidden population of cosmic assassins. The search was no longer just about academic curiosity. It had become a matter of profound existential importance. We had just learned that our solar system is not an island, but a vessel navigating a dark and treacherous ocean, an ocean populated by predators we are only now beginning to comprehend. The ghost was real, and now our urgent vital mission was to find the others before they found us. And so the ghost in the machine was revealed. The impossible flash, the gamma-ray signal that defied all of our known physics, was not a weapon, nor was it a message from an alien intelligence. It was something far more primordial, a voice from the cosmic graveyard. The light we captured was the violent, echoing death rattle of a star that had perished millions of years before 3I, Atlas, ever began its lonely pilgrimage through the dark. It was the last furious expenditure of energy from a fragment of a magnetar's core, a celestial cinder that had carried its own apocalypse within it, waiting for the gentle heat of our sun to finally unlock its ancient fury. The case, it would seem, was closed, yet in finding the answer, we had unlocked 1,000 new questions, each one more profound than the last. The end of one mystery had become the birth of a new and unsettling science. We stand now in the quiet afterglow of that discovery, looking back on the frantic, exhilarating, and often bewildering journey that 3I Atlas led us on. It feels like a lifetime ago that this object was just another faint smudge on a digital plate, another alphanumeric designation in a vast and swelling catalogue of cosmic wanderers. It was an object of curiosity, certainly a rare visitor from beyond the heliosphere, but it was a passive one. We expected it to be a time capsule, a pristine frozen relic from another star's nursery, offering us a quiet glimpse into the building blocks of a planetary system we would never see. We prepared our telescopes to study its chemistry, to analyze its dust, to gently probe its secrets as it swept past. We believed we knew the rules of this encounter. The universe, however, had other plans, and it delivered its lesson with the force of a supernova. When that burst of gamma radiation erupted from what should have been a placid, slowly sublimating block of ice and rock, it did more than just overload our detectors. It overloaded our understanding. For a breathless moment in human history, we were confronted with an event that simply should not have been possible. You remember the confusion, the cascading alerts across the globe, the frantic search for a conventional explanation that refused to materialize. Every known law of astrophysics screamed that a comet could not do this. It was as if we had watched a drifting iceberg suddenly detonate with the power of a thermonuclear bomb. The disconnect was so absolute, so jarring, that it forced us to tear up the very blueprint we thought we had for the cosmos. We were explorers who had discovered a new continent, only to find that the very ground beneath our feet was rewriting the laws of geology. This single transformative event has forever altered our perception of the space between the stars. Before 3I Atlas, we viewed the interstellar medium as a place of serene emptiness, punctuated by silent, inert travelers. We saw objects like Oumuamua and Borisov as messengers of creation, fossilized remnants from the birth of other solar systems. Now we are forced to confront a far more dramatic and violent reality. Interstellar space is not just a nursery, it is also a cemetery. It is haunted. It is teeming with the shrapnel of cosmic cataclysms, with the shattered, volatile remains of dead stars and obliterated worlds. These objects are not merely messengers of birth, but are sometimes carriers of death, containing pockets of unimaginable energy, ticking time bombs, drifting silently for eons until they happen upon an unsuspecting star. 3I Atlas was not a time capsule. It was a ghost ship carrying the phantom echo of its own system's violent demise. This realization sends a shiver down the spine of astronomy. It recasts every future interstellar visitor in a new and startling light. We can no longer assume they are benign. Each new object that crosses the threshold of our solar system must now be treated with a new kind of scrutiny, a new level of suspicion. Is it a simple comet? Or is it a fragment of a neutron star merger? Is it a rogue planet? Or is it a piece of a world torn asunder by a black hole? The discovery has injected a thrilling and terrifying new element of the unknown into the search for these objects. We have learned that the universe is not only more clever than we imagine, it is more clever than we can times imagine. And 3I Atlas was its profound, explosive lesson in humility. It stands as a monument to the idea that the most important discoveries are not those that confirm what we know, but those that shatter what we believe. This was a profoundly human journey as well. We witnessed science unfold not as a dry textbook exercise, but as a messy, passionate, and collaborative global drama. We saw rival teams set aside their differences, sharing data in real time across continents and time zones, united by the sheer impossibility of what they were seeing. We saw theorists work feverishly for sleepless weeks, their whiteboards filling with beautifully complex equations that were one by one proven wrong by the stubborn reality of the data. This process, this constant cycle of conjecture, testing, and failure, is the beating heart of scientific progress. It is a testament to our species' unyielding refusal to accept the inexplicable. We will beat our heads against the walls of ignorance until they crumble, and what we find on the other side is always a universe more spectacular than the one we knew before. The legacy of 3I Atlas, therefore, is not merely a new classification of celestial object. Its legacy is a fundamental shift in our cosmic perspective, a permanent alteration of our relationship with the Great Void. It is a pivotal moment, a line in the sand drawn by a flash of gamma rays. Future historians of science will likely speak of astronomy in two distinct eras, before Atlas and after. Before, we were passive observers of a largely predictable clockwork universe. After, we have become detectives in a cosmic crime scene of unimaginable age and scale, knowing that the clues to the most violent events in the universe are not just light years away, but maybe drifting right through our own cosmic backyard. We have been awakened to the fact that the history of the galaxy is not just written in the stars, but is carried in its debris. To rise to this new challenge, we cannot simply continue as we have before. A new kind of astronomy is required, one that is faster, smarter, and more vigilant than ever. The future of this search, the hunt for the next 3i, Atlas, is already taking shape on drawing boards and in mountain observatories around the world. The vanguard of this new era is a marvel of modern engineering, nestled high in the Chilean Andes, the Vera C. Rubin Observatory. For 10 years, this 8,400-pound eye will scan the entire southern sky every few nights, cataloguing billions of objects and detecting millions of changes with a speed that was once pure science fiction. Its great survey of space and time is not just about creating a static map, it is about creating a dynamic film of the living, breathing cosmos. Crucially, in the wake of our interstellar visitor's shocking revelation, the mission parameters for the Rubin Observatory have been profoundly enhanced. Software is being written right now, a new set of complex algorithms designed with a singular purpose to hunt for ghosts. This initiative, nicknamed the Atlas Protocol, will sift through the petabytes of data the observatory generates every single night, looking for the telltale signatures of interstellar trespassers. It will flag objects with unusual trajectories, with hyperbolic orbits that prove they are not bound to our sun. But it will go further. The protocol will cross-reference these candidates with data from every other telescope on and off the planet, looking for the slightest hint of anomalous energy signatures, for chemical compositions that defy a simple cometary origin, for any deviation from the expected that might suggest a more explosive nature. When the Atlas protocol finds a credible target, it will trigger an automated global alert system, a celestial fire alarm for the world's astronomers. Within minutes of detection, the coordinates will be broadcast to a network of rapid response telescopes. These are not the giant, slow-moving behemoths of old. They are agile, robotic instruments designed to slew across the sky in seconds to fix their gaze on a new target and begin collecting data before the initial discovery has even been fully processed by a human. The goal is to create a seamless planetary-scale defense grid of observation, a system that ensures no interstellar visitor can ever again slip past us without undergoing the most intense scrutiny imaginable. We will know they are coming, and we will be ready to watch their every move. Of course, observing these objects in visible light is only half the battle. The true lesson of 3i, Atlas, was that the most important secrets are often screamed in wavelengths our eyes cannot see. To that end, a new generation of high-energy sentinels is being designed, conceived specifically to listen for the whispers of gamma-ray bursts from sources that were previously thought to be silent. The prevailing wisdom was to build gamma-ray telescopes with narrow fields of view designed to stare deeply at known energetic objects like galaxies with active black holes. But 3i, Atlas taught us that the threat can come from anywhere, from an object that looks completely innocuous. So the next wave of gamma-ray astronomy will focus on all Sky Monitor's instruments with a fisheye view of the heavens, constantly watching in every direction at once. Imagine a constellation of small, dedicated satellites working in concert to form a single planet-sized gamma-ray observatory. An event detected by one satellite can be instantly triangulated by the others, pinpointing its location on the sky with unprecedented accuracy. This is the dream of projects like the proposed Cosmic Anomaly Tracker Array. Such a system would be our early warning network. It would detect a burst and within a fraction of a second provide the Atlas protocol and the robotic ground telescopes with a precise location to search for an optical counterpart. Had such a system been active when 3i, Atlas, let out its dying roar, we would have had simultaneous multi-wavelength data from the very first moment of the explosion. The frantic detective work we had to undertake would have been a real-time diagnosis. This is the future, a fully integrated multi-messenger nervous system for Earth, capable of detecting and analyzing any strange new light in the sky, no matter how fleeting. This new hardware, this global network of digital eyes and ears, represents a monumental leap forward. But perhaps the most profound changes are happening not in the mountains or in orbit, but in the minds of theorists and on the supercomputers that model our universe. A whole new field of study is being born from the ashes of our old assumptions, a discipline some are beginning to call interstellar forensics. It is the science of sifting through cosmic debris to reconstruct the cataclysm that created it. Scientists are now running complex simulations, modeling the chaotic explosions of magnetars and hypernovae with stunning fidelity. They are trying to understand how a fragment of a stellar core could be ejected, what kind of energies it could contain, and for how long it could carry that latent charge as it tumbled through the void. They are asking questions that just a few years ago would have sounded like fantasy. What other kinds of stellar shrapnel might be out there? Could fragments of white dwarf stars packed with dense, degenerate matter be wandering the galaxy? What about splinters from the merger of two neutron stars events that forge the heaviest elements in the universe? Could we one day capture the visitor that is made not of water ice and carbon, but of pure gold and platinum? The possibilities are as tantalizing as they are mind-boggling. Every simulation that produces a viable energy-storing fragment, like 3I Atlas, opens up a new chapter in the cosmic playbook. We are, for the first time, studying the anatomy of stellar death, not by looking at the distant blurry event itself, but by getting our hands on the physical evidence millions of years later. This new theoretical framework is also powering a grand re-examination of our own past. Astronomers are now engaged in a form of data archaeology, digging back into the archives of every observation made of our first two confirmed interstellar visitors, Oumuamua and Borisov. They are looking at the old data through a new lens, the lens of suspicion that 3I Atlas provided. Was Oumuamua's strange tumbling motion and slight non-gravitational acceleration really due to outgassing? Or could it have been a sign of something stranger, a clue we simply weren't equipped to interpret at the time? Was Borisov's composition truly that of a simple, pristine comet, or were there subtle chemical anomalies we dismissed as noise? We may never know for sure, but the search itself is changing how we approach the data. We are no longer looking just for confirmation of the familiar. We are actively hunting for the signature of the alien, the exotic, and the explosive. Ultimately, this is where the journey has led us. It has taken us from a single anomalous point of light to a complete revision of our place in the galactic ecosystem. We have been forced to see our solar system not as a secluded island, but as a busy harbour on a vast interstellar ocean, a harbour through which all manner of strange and wondrous vessels may pass. Some will be simple rafts of ice and dust, relics of peaceful creation, but others will be the wreckage of distant, terrible storms, carrying within them the memory of fire and destruction. Our task is to build the lighthouses, to post the sentinels, and to learn the language of these visitors, whether they whisper of creation or scream of annihilation. The story of 3I Atlas is now woven into the fabric of our scientific heritage, a cautionary tale of cosmic violence and a beautiful story of human ingenuity. It serves as a permanent, humbling reminder that just when we think we have the universe figured out, it will find a way to surprise us, to delight us, and to terrify us in equal measure. The sky above you tonight is the same sky we have always known, but it is not the same place. It is deeper, more mysterious, and filled with more potential wonders and dangers than we ever dared to dream. The hunt has just begun. And as we cast our new wider nets into the cosmic dark, we can only wait and wonder what other impossible things are already on their way.